Okay, welcome to lecture 3. What we'll be doing in lecture 3 is basic probabilities and how do we group the data to summarize the data. Okay. So these are the two main topics that we're covering. We'll be covering some basic probability theory concepts. What are the major definitions in probability? What are mutually exclusive and independent events? Very importantly, we have to take note of what is conditional probability. This will be something new to you. Mutually exclusive and independent events will be something that you have covered a little bit in secondary school. Okay, conditional probability is something new totally. Then we'll talk about data summary. How do we use contingency tables, which you have already seen in lecture 2? How do we use those tables to calculate proportions, relative risk, and odds ratio? These are the important measurements that we need to learn how to calculate. Okay, we come to some of the major definitions in probability. The most important part is this concept known as sample space. Sample space is denoted by S. It's basically all the possible outcomes of an experiment. Okay. So let's say the sample space for weather could be raining, sunny, windy, every single possibility. So those are all the possibilities. And then a subset or a part of the sample space is what we call an event. That means raining is an event of weather. Sunny is an event of weather. Okay. So for every single event, we assign a number between 0 and 1. Percentage-wise, that is also known as a probability. Okay. When an event has a probability of 1, that means 100% it will happen. An event of a probability of 0 means there's no chance that it will happen. Okay. So that gives us a precise measurement of how likely is an event happening inside the whole sample space. Very simply, we can denote probability as the number of times that an event A can occur divided by the total number of possible probabilities, possible outcomes. Sorry. Okay. So for example, if you have a deck of poker cards, okay, so the probability of drawing ace is 4 out of 52 or 1/13. So that is the probability of drawing an ace. But what is the probability of drawing any card that is a spade? So there are 4 suites, so it's actually 13 divided by 52, so in 1/4. Okay, so that is the probability. Okay, so consider another example, which is your regular dice or die. One singular is called die. There is 6 possibility, 1, 2, 3, 4, 5, 6. So the event space is 1, 2, 3, 4, 5, 6. So let's say that you are only interested in even or odd number. The sample space is even number or odd number. So the probability of getting an odd number is you get 1, 3, or 5. So the probability of getting an odd number is 3 out of 6. Similarly, the probability of getting an even number is 3 out of 6, which is half. Okay. So the basic concept with probability is just the number of events that can happen divided by the total number of events. That is the probability of a certain event happening. This is what we have mentioned in words just now. Probability has to be between 0 and 1 inclusive. Okay, the probability of any event happening has to be between 0 and 1 inclusive. 0 means that there is no probability of this event happening. 1 means there's 100% of this probability of this event happening. Okay, so when there's a sure event, 100% possibility or probability, the probability equals to 1. When it's an impossible event, the probability is 0. So indirectly, it also means that point 4, the larger the probability, the more likely the event is likely to occur, or the more likely the event will occur. Okay. Okay, the next concept that we have to discuss is this thing known as complement. So complement, let's say you have A. So complement of A is usually denoted as A prime. It basically means that the event that A does not happen. Okay. So essentially, complement just says that the probability of an event A happening and the probability of, or rather the probability of event A happening, or the probability of event A not happening, that's a complement of A, will be equals to 1. When something happens plus something not happening is equals to 1. Okay. So usually complement law is for us to find probability of an event that we do not know. But the event not happening is actually quite readily known. Okay. So this is one way to use it. Okay, we can represent sample spaces and probabilities in a few different ways, in fact, three major methods. The first one is a Venn diagram. So sample space is always denoted like a square. In your secondary school, you call that as a universal set. Okay, so probability of A happening is where we shade the probability of A, and then let's say there's an intersection of B. Probability of A happening is the entire circle of A. We don't really care about B. Okay, so on the other hand, we also know that what is the unshaded part of B, that is the unshaded part of A in the whole box, that is the complement of A. Okay, the probability can also be represented as a tree diagram. Personally, I would prefer a tree diagram because it's easier to visualize. Okay, so let's say we start off with 7 items, 3 white balls, no, 3 black balls, 4 white balls. So the probability of drawing a single black ball is 3 out of 7. The probability of drawing a single white ball is 4 out of 7. Okay, so from here, we can actually then look at what is the probability of drawing a white ball, a black ball first, and a white ball, because you have 3 out of 7, so 3 out of total 7. Then the second probability, you've already drawn out the black ball, you're left with 6 balls. Okay, but here there's still 4 white, 2 black. So the probability of drawing a white ball is, in this case, 2/3, 4 out of 6. Okay. So the probability of the event you can just multiply up, which means that the probability of drawing a black ball and a white ball is 3 times 7, 3 over 7 times 4 over 6, and so on. So you can start to draw all sorts of probabilities in this case. Okay, give you a bit of time to look at it. We go to the last one. Let's say you want to draw 2 white balls, one after another. Okay, what's the probability of that happening? From 7 balls, the probability of drawing 1 white ball is 4 out of 7. Now you're left with 6 balls. 3 black, 3 white. The probability of drawing another white ball from this 3 black, 3 white is half. So the probability of drawing 2 white balls is first 4 out of 7 multiplied by 3 out of 6. Okay. Okay, the third method is what we call as a probability diagram. Essentially, it's just listing out all the possible outcomes of an experiment. So let's say when you want to throw 2 coins, you have either 4 possibilities: head head, head tail, tail head, or tail tail. Okay, so essentially this is what it does. If you have 3 coins, then you have head head head, head head tail, and so on and so forth until you go to tail tail tail. Okay, so as you can see, the more items that you have, it will become very tedious for you to list out all the possible outcomes. Okay. Okay, so how do we use the 2 coin example? Flip 2 coin example using a Venn diagram, a probability diagram, and a tree diagram. Okay, so the first one we'll go through on the next slide is your Venn diagram. So in Venn diagram, since these 4 outcomes do not overlap each other, it's just your head head, head tail, tail head, and tail tail. Okay, that's all. Or solution A. This is solution A in Venn diagram form. However, in the probability diagram form, we have seen that in the previous slide, you have first coin head, second coin head, will give you head head. First coin head, second coin tail will give you head tail, and so on and so forth until you get tail tail. What is more useful, and as I said before, I personally prefer a tree diagram. Okay, so you have a first coin and second coin. The first coin, the probability of getting a head or a tail is half each, 0.5, 0.5. When you throw a second coin, the probability of getting a head and a tail is also half. Okay, so which means that the probability of getting two heads is actually 1/4. The probability of getting a head tail is 1/4, tail head is 1/4, tail is 1/4. Okay, so however, if I don't care whether is it a head tail or tail head, then the probability of getting different outcomes for two different coins is one is half, because you have two possibilities out of four. Okay, for this example 3, let's consider the situation of flipping two fair coin. The term two fair coin is important because it tells us that the probability of head or tail is half, 0.5 each. So what is the probability of both coins having heads up? Okay. So given a sample space, there are only four possibilities. So there's only one time both head is occurring. Okay, so it's actually 1 out of 4. So it's 1/4. What is the probability that only one will turn head up? Okay, so only one head. That means you have head tail or tail head. So there's actually two possibilities. Okay, so it means that there's two outcomes out of 4 in total, which is half. Okay, the next thing we consider is when we have two different events or two of the same events. Okay, just two events. Okay. We have two concepts here. One is called the union, one is called the intersect. Union is simply you have either or. Let's say the probability of raining or sunny. Okay. Intersect is and. That means the probability of raining and sunny. Intuitively, we already know that given any day, the chances of it being a rainy day or a sunny day is much higher than it being a rainy day and sunny day. Okay, this is where we want to find the difference. Okay, so let's look at how do we draw them in a Venn diagram. For example, I just, instead of A and B, I list A as sunny and B as rainy. So union, in this case, this is a union. Okay, this is A or B. When there is a union, it means that it can either be a sunny day or rainy day. The probability is much higher. Okay. However, on this hand side, this is A and B, which means that it is both sunny and rainy. Okay. So the probability is much lesser. It's just this overlapping part. So what I want you to think about is what happens to this area here, this empty area. It simply means that it is neither sunny or rainy. That is the complement of A union B, essentially. Which can be maybe overcast. Okay? So we can actually use these probability events for a lot of different things. Okay, so let's look at example 4. Example 4 is a bit more complicated or more messy. A fair dice is tossed. So a fair die simply means that the probability of getting any of the 6 number is 1/6. So A is the event of getting an even number. So A is an even number. B is the event of the number divisible by 3. So find probability of A, probability of B, probability of A union B, probability of A intersect B. So the sample space is essentially the same. It is 1, 2, 3, 4, 5, 6. Okay. Event A, even numbers, happens in your 2, 4, and 6. So the probability of an even number, so this is an even number, is 3 out of 6. Because it's 2, 4, and 6 out of 1, 2, 3, 4, 5, 6. So it's half. Similarly, the opposite, the probability of getting an odd number is also 3 out of 6. Okay. However, look at these 6 numbers. What is the probability of these 6 numbers divisible by 3? It is only item number 3 and item number 6. Only these two numbers are divisible by 3. So the probability of B is 2 out of 6 chances. So it's 1/3. Okay. So which means that when you construct an intersect, the probability of getting an even number and it is divisible by 3. There's only one answer. Even number and divisible by 3. So 3 and 6. Which one is divisible by 3? Only 6 is divisible by 3. Correct? So it is 1 out of 6 chances. So it's 1/6. Okay, so we get that. However, the probability of an even number or a number that's divisible by 3. Okay. So which one is even and which one is divisible by 3? Okay. Is 1 even and divisible by 3? Okay. 1 is no. Is 2 even or divisible by 3? Yes. 2 is. Is 3 even or divisible by 3? 3, yes. Is 4 even or divisible by 3? 4, yes. Is 5 even or divisible by 3? 5 is not. Is 6 even or divisible by 3? 6 is also. So you have 4 outcomes out of 6. So that's 2/3. Okay. When we say that two events are mutually exclusive, it means that these two events cannot happen at the same time. Okay. So the intersection is actually 0. There's no intersection. These two events does not overlap. For example, we cannot have both day and night at the same time. Okay. Neither can any one of you be genetically male and genetically female at the same time. You can have only be either one. Okay, so that's mutually exclusive. Okay, for this example 5, let's say that two fair dice are thrown. Okay, so A and B. A is the event whereby the sum of the dice is even. B is the sum of the dice is 11. Okay, what is the probability of getting a total score when you throw two dice that is both even and 11? Now, without going through the mathematical logic, the mathematical calculation behind, you know that you cannot have the possibility of having an even number that is also 11. 11 is not an even number. So in this case, these two events are mutually exclusive. The probability of having a total score that is both 11 and even is 0. Okay. When we say two events are dependent, it means that the occurrence of one event does not affect the occurrence of another event. So for example, I throw a dice twice. Okay. The outcome of the first throw does not affect the outcome of the second throw. Correct? So let's say I want to find out what is the probability of getting 2 ones. The first throw I get a 1. The second throw I also get another 1. Okay. So the first throw I get 1. The second throw I get a 1. Okay. So I know that the probability of getting a 1 is actually 1/6. Okay, because there are only 6 possibilities. The second throw is also 1/6. So the probability of throwing the same dice twice and get 2 ones, I just multiply it up and get 1/12. Alright, so this is how we can use independent events. Okay, so let's consider this example. Let's say a sample space A, B, C, D, E, F, G, H. So there are 8 items in all. Okay, A is A, C, E, G, B, and so on, so forth. Okay, is every event of X independent of A? How about events X and B or X and C? Okay, so we don't bother about the first part. How do we actually calculate this second portion? Okay, this is a more important one. The first part we leave it aside. The actual mathematical calculation is in the next next two slides, which I will not go through in detail because it's more important to care about event X and event B, or event X and event C. Just look at these numbers alone. Between B and X, what is the commonality? The commonality is only G, correct? Between C and X, the commonality is only G. So the commonality is only 1 out of 8. So the probability, here I write the probability of X and probability of B is actually 1 out of 8. Same thing, the probability of X and the probability of C is 8 equals to 1 out of 8. So, okay, all right, because there's 8 in total. Okay, so far so good. So for next two slides, actually is to go through this step, but I will not go through the maths details of it. This is actually not that critical. Okay, this is a very important topic and is also a pretty confusing topic called conditional probability. Conditional probability means A, the probability of A happening given B. Okay, so how do we read this? It means that the probability, how do you read this symbol? There's a probability of A bar B. It means that the probability of A happening given B already known. So the calculation or the formula is A and B divided by the probability of B happening. So this is the equation that you have to note. Always take note that the probability of A given B is not the same as the probability of B given A. Okay, so if I write out the probability of B given A, we will see that the numerator is the same. It's a probability of A and B, but the denominator is the probability of A. Okay, it's different from here. Okay, let me just show it. It's actually different from this. These two are different, so take note. Okay, so let's look at this example. Assuming that the probability of raining day in Singapore is 0.2. So let's write out probability of rain is 0.2. Okay, which means that the probability, why is my hand, let me just get this off. Okay, which means that the probability of no rain or sunshine is 0.8. Correct? Eraser again, erase myself. Okay. And John travels to school via either taxi or public transport. But you know that the probability of him taking a taxi on raining day and the probability of him taking a taxi on sunny day. Okay, so this is important. So what is the probability of John taking a taxi to school? What is the probability of John taking a public transport given that it's raining? So it's basically asking you, okay, now it's already raining, but John has not come to school yet. What is the probability that he will take a public transport? You already know that it rains. Okay. On the other hand, if it is a sunny day, or rather, the third question is, what is the probability that it's a sunny day given that John has taken a taxi to school? So let's say you're in class now. John comes in and says, okay, he has taken a cab to school and it's so expensive. What is the probability that it is a sunny day outside? Okay, so we want to find out the first question, the probability that John will take a taxi to school. So John taking a taxi to school comes from two different things. John taking a taxi to school on a rainy day, or John taking a taxi to school on a sunny day. So there are two probabilities. Okay. So you have both of them, it gives you 0.22. Alternatively, we'll use a tree diagram. It's much easier to draw it out if you can, so that you don't make mistakes. Okay, so here is a tree diagram. This is John. Okay, so it's raining and sunny. Taking a taxi to school comes from two different things. He takes taxi to school at two different occasions. Okay, because if it rains, he has 70% of chance taking a taxi to school. But if it's sunny, well, he may find that it's too hot and he have 10% of chance taking taxi to school. So you add up these two probabilities. Okay, that gives you your 0.22 as we see in the previous slide. Okay, we come to the next part. What is the probability that John will take a public transport when it is raining? Okay, so we want to look at, given that it's raining, given that it's already raining, what's the probability that John will take a public transport? This means that, well, when you're coming to school, it's already raining. So what's the chances that John will take a public transport? Okay. The numerator is public transport and raining. So you go back to a previous slide, look for public transport and raining. That gives you 0.2 times 0.3. And the probability that it's raining, because 80% is sunny, 20% is raining. So you get 30% of a chance that John is likely to take a public transport given that it's raining. Okay. So it also means that when it rains, when you know that it's raining, the chances of John getting a public transport taxi is actually 70% of a chance. Okay, so we go to the third part of the question. What is the probability that it's a sunny day given John takes a taxi to school? Okay, so let's say you're in class. John walks in and is complaining about how expensive it is, that he has a traffic jam in his cab or something like that. What is the chances that it is a raining day outside? First, you have to go back to what is the probability that John is taking a taxi and it's sunny. It's also the same thing as it's sunny and taking a taxi, or taking a taxi and sunny. It doesn't make a difference. Okay, so when you go to the diagram, the tree diagram, you find that is 0.8 times 0.1. And to take a taxi, we found that this number out 0.02 from your part A. Correct? We found this on part A. So you just divide it, you have 1 divided by 11. The only thing is, this part, taking a taxi, is not directly from the diagram itself, from tree diagram. You find it from part A, because it consists of two components, remember? Okay, let's look at question 8. Question 8 will require more information from your genetics. Okay, so I'll go through the important parts, then I'll encourage you to look through this example a few times, especially with this example and question, example 7, the John example. Look through how you do your conditional probability. Okay. So we know that a male with homozygous dominant, AA, both capital A, with a female of homozygous recessive to produce a F1 offspring. Okay. So if homozygous dominant and homozygous recessive will only produce one offspring, that is heterozygous dominant. If two of these heterozygous dominant, this is your F1. Okay, this is your F1. If you take F1 times F1, which is it. Let me just erase off all this. Which is technically equivalent to AA times AA. That gives you your F2. So what is the probability that F2 has a dominant trait? So we can actually just look it up. Okay. You can just draw what's the possibility of all the F2s. This again. Okay. So F2 will have the probability, will have either AA, 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 or AA. So which are the dominant trait? These three. So you have 3 out of 4 dominant traits. So it's actually 3/4. Okay, so we have done technically this question already. Now, this answer for part question example 8, part A is actually given on the next slide, but we have done this already. So what is the probability that a particular offspring is F2 from the F2 generation is heterozygous given there's a dominant trait? So you know there's a dominant trait. Because dominant trait is you can see, is visible, and it is heterozygous. So basically, I'm telling you that I have only given you these 3. What is the probability that is a heterozygous? Isn't that, let me find a purple color, isn't that these 2? Correct? So you end up with 2 out of 3. Make sense? Because I only give you 3. I pull out the 3. The homozygous recessive from F2 is already out of the question. Make sense? If a male with a dominant trait from F2 is mated with a homozygous recessive female and they have an offspring, so what's the probability? The offspring of with dominant trait, what's the probability that the male is heterozygous? That we come to the next part. Okay. But at least we get these 2 first, part A and part B down. Okay, so this is for question 1. Question part A and part B. Now, essentially, you have 4 outcomes. Correct? So this is already the F2. 4 outcomes already. Which one are dominant? So you want to find the probability of dominant. The dominant ones will be, let me check this, and this. On the other hand, this guy here is recessive. So you end up with 3 out of 4 dominant. Okay, so you have 3 out of 4 there. For part B is, if you are given dominant trait only, so dominant trait already, so I pull out, which are the dominant trait? These 3, right? You have AA, that's dominant trait, another 2 AA, 1 big A, 1 small a. So you have 1 homozygous, 2 heterozygous. So you have 3 of them. These are 3 dominant. How many of these are heterozygous? Okay, what you see is you have 2 out of the total of 3. Isn't that what you get here? So heterozygous and dominant, you look at the diagram here, heterozygous and dominant is essentially this. Correct? Dominant trait is 3 of them. That gives you an answer. Okay, if you can understand part A and part B, it is good enough. Part C is for those of you who want a bit more to challenge yourself. Look through whether can you work out part C yourself. Otherwise, please go back and go through the whole series of conditional probability. Make sure you get it right. That is very important for this chapter, conditional probability. So I will leave part C for yourself to do. To me, is not that critical in your syllabus. Okay, you don't really have to know, but just look through if you have the time. Okay, we come back to contingency table. That's where we left off in the previous lecture. So remember, a contingency table is a way of tabulating your count. A few things to take note. The rows represent the treatment or risk factor. So in this case, the risk factor is whether the pregnant mother is a smoker or not. The out column represents the disease state. So the infant weight is the status. Just erase something. Okay. All right. Now you can actually see that out of 74 infants that's born by smoking mothers, 30 are of a smaller weight. out of 115 born by non-smokers, 29 are smaller weight. Okay, so you can actually, based on this, look at what is proportion of smokers and non-smokers. However, more importantly, what we can also say is, so we can first we state this. The proportion of smokers is actually 74 divided by total 189. So how many what's the ratio of smokers we have? 74 divided by 189. We get about 39.2. About 39.15, 39.2%. Right? But what is also useful is this. Can I look at the sample proportion? So can I ask you, what is the proportion of smokers and small babies, smaller weight babies? So you have 30 divided by 74, correct? So it's 30 divided by 74. That gives you 0.405. I can also ask you the opposite. What is the proportion of non-smokers or babies, small babies that's from non-smokers? Okay, so you have 29 divided by 115. So that gives you 25.2%. Now, just by looking at these proportions, you can tell that the chances of having a smaller baby if the mother is a smoker is much higher than that of a non-smoker, correct? So this is what, okay, let me just highlight. This section is what we call as your sample proportion, which in fact, this is also a sample proportion. Okay, we'll go through that in your next slide. Alright, this is precisely what we did calculation in the previous slide. Sample proportion is a summary statistics looking at categorical variables. So essentially, this is your smoker mothers, the proportion of smokers and smaller babies. This is the proportion of non-smokers and small babies. Okay. So we have done this calculation already. We will not go through again. If you want, you can go back to your previous slide to look at it. So when we have these two proportions, we can actually just look in a very simplistic sense. It means that the probability of having a smaller baby is 15.3% chance higher if the mother is a smoker, correct? So this difference can be quite substantial. You're talking about every 100 babies, there's 15 of them having lower weight, and it may need medical care, more intensive medical care. So what we want to do is, are there a better way of evaluating it? This is what we go to a next part. We are talking about risk, relative risk. So what's the relative risk of having a smaller baby if the mother is a smoker or non-smoker? Okay, so relative risk is a ratio. It basically tells us how much more risk what's the proportion of more risk a person have if you have a certain factor. So in this case, we have two boxes here. Okay, A and B is a total number. C and D is a total number. Okay, so that's what we have. So essentially, we are taking the proportion of smoker and small babies divide by the proportion of non-smoker and small babies. essentially what we are doing is we are using the proportion of smokers but still having small babies as a control. So that gives us this thing known as a relative risk, or RR. That's just a number. However, how do we interpret relative risk? Now, relative risk of 1. Okay, so we have to remember that relative risk, there is a numerator and a denominator. Okay, so relative risk of 1 means that the proportions are the same. There is no risk between the two different groups, correct? So in this case, when relative risk equals to 1, it also means that the numerator equals to denominator, right? When relative risk is less than 1, how do you get relative risk of less than 1? Means that the numerator, here I just write it here, the numerator has to be smaller than the denominator to get relative risk of less than 1. Okay. Which means that the event is less likely compared with the other. Okay. Relative risk of more than 1 is the opposite sense. That means the numerator have to be larger than the denominator, which is in our smoker's case just now, relative risk is above 1. Correct? Okay, however, for relative risk, we realize that very often the proportion of people having a disease is much smaller than the proportion of people not having a disease, correct? So if we write it out, will be the proportion of people having a disease or condition divided by the proportion of no disease is actually very low, correct? It should not be equal, otherwise you will be in big trouble as a society. In fact, this number should be pretty close to 0, hopefully. Which also means that if that's the case, A is those that have the condition plus B is almost equals to B. C plus D is almost equals to D. Almost equal, approximate. Okay. In fact, I should really say that this is, let me just erase this. I will say that this number is close to 0. Okay, or very low. Okay, otherwise as a society we're in trouble. So if it is the case, can we simplify risk ratio into another thing? So we take, every time we see C and D, we just take it as your D. And every time we see B and C, we just take it as B. So we will end up with a simplified ratio known as a odds ratio. Okay. So very often we report odds ratio as the odds of having a disease. Odds ratio is what is the probability of getting a disease. So it is an easier estimation. We don't really need the other two. Okay. Now it's a measure. Of course, very often if you have all the numbers, you can report the relative risk and odds ratio. In fact, these two, the real case scenario, often lies in between the relative risk and odds ratio. Okay. So odds ratio can be seen as the lower end of relative risk. Okay, the interpretation of odds ratio is the same as your relative risk. If the odds is equals to 1, means the numerator is the same as denominator, there is no association with the risk factor relating to the disease state or disease condition. If it's more than 1, that means the factor in having a risk increases the probability of having a disease. If it's less than 1, having a factor decreases the probability of having a disease. Okay, so how can we use risk and odds ratio? Which one is suitable? Consensusly in the scientific society, we say that odds ratio can be used for all sorts of studies, your cohort studies and case control studies. But relative risk, we tend to use it only for cohort studies. Case control study we still can use relative risk, but it is an overestimation. Okay, so that is why we seldom use relative risk in a case control study. We just calculate an odds ratio. Okay, we do not want to overestimate our situation. With that, that comes to the end of lecture 3. So thank you very much. Have a nice day.